Okay, here we are now to learn the line coding, that is also we call it as the data formats. What a data formats is, they are the different formats which are being used for the digital data, so that if there are any errors at the receiver side can be detected if you are converting into a typical format, right? As well as the properties of the data formats are designed in such a way that the bandwidth as well as the energy which is required for the signal is nothing but maintained, so that during transmission then bandwidth is maintained as well as the energies of the signal is being maintained. So you have different properties of the line codes which you need to go through. As we are going to just see the practical aspect of line codes, we are starting with that is the different line codes over here. What are these? The different line codes. One line code is what you call it as a unipolar. Now what does unipolar stands for? Any line code can be converted, or any data formats when you are converting it, it will be converted into amplitude, that is 3 amplitude. One is it's a unipolar, it's a bipolar, right? Or it is a polar. Now polar is, unipolar is plus A amplitude, polar is plus minus A by 2 amplitude, and bipolar is plus minus A amplitude, correct? Now either it will be converted into energy wise into unipolar, polar or bipolar, and as per the bandwidth wise or time wise it is being converted as it is written, that is RZ, written to 0, or it is NRZ, that is non-written to 0. So any format can be unipolar RZ, NRZ, polar RZ, NRZ, bipolar RZ, NRZ. There is an additional we'll say a format which is being called as a split phase Manchester, which is either we call it as a split phase or we call it as the Manchester. So this is an additional, we'll go to it. The first property of a format, that is a data format, the data has to be transparent so that you can convert it into a typical format itself, right? Now you have a data generator which has been shown over here. What is this data generator? It is generating a typical pattern. You have two patterns, P1 and P2. Any one of the pattern you can use. Now here the first pattern which we can see is 1 with the 4 zeros. How do I understand that this is a 1 with 4 zeros which are representing? Now see here. What I can see is the duration which is going to be lasting for that particular one duration. So how much it is? It is 1 centimeter approximately on the DSO, right? Now what you have is 1, 2, 3, 4. So there are 4 centimeters which are representing 0, and once again it is repeating to 1. So what is this pattern repeating is 1 and 4 times 0. So the pattern is repeated after 5 bits itself, correct? So instead I have a second pattern also. So we'll be observing the second pattern. What you have the second pattern is here. The second pattern is 1 centimeter, that corresponds to 1, then it is a 0, then again it's a 1, and then there are 2 zeros which are being there. So what is this pattern? 1 0 1 00 is the pattern which has been there. Did you understand? Now we'll come to the formats which we are going to observe for. So what are the different formats here? As I said, unipolar, polar, bipolar and so on. So what we'll do is we'll apply this pattern as an input to this particular formatting circuit itself, right? Now first format is a unipolar RZ format. Now we'll observe how is the unipolar RZ. Unipolar is polarity which is plus A, RZ is written to 0. What does written to 0 means is between the digital, that is logic 1, the format is going to return to 0 in between the logic 1. So see, what you have is the waveform. Let's observe the waveform. Right. So what does the waveform say? See, as I said, return to 0 format. So return to 0 is in between logic 1, the format returns to 0. So here what you can see is the format returns to 0 in between, what you can say is the logic 1. So logic 1, it is, that is logic 1 for TB by 2 duration. For 0 it is 0. Again for next one it is TB by 2 it is 1. Next 0 it is 0, and again TB by 2 it is nothing but logic 1. Correct? Now we'll see what you need to measure. You need to measure is the TB duration, as we can once again say measure. Then you come to the option that is cursor. In type or in the channel, if I say source 1, and in type I'll say amplitude, that is time, and I'll adjust the cursor. So my first cursor is being placed over here. Then I'll press the cursor 2. Where is the cursor 2? Yes, the cursor 2. I'll place the next cursor over here. What is the duration of the TB? The duration of TB is approximately, that is 1 milliseconds is the duration. Now what I need to measure the duration of the return to 0 format, that is unipolar return to 0 format. I'll bring the cursor over here. Now what you can see is, yes, it is 500, that is microseconds. Once again we'll just move it and we'll say 480 microseconds, that is nothing but corresponding to that is 500 microsecond, that is 0.5 milliseconds, which you can observe for. So it's exactly correct. Now the second part of the format is observing the spectrum for the formats itself. So for spectrum, what you need to do is you go to the math function of the DSO. On the math function, you have the operation which has been shown over here. What does the operation show is? It shows the negative, the positive, the addition, multiplication, and so on. What I need is the FFT, that is fast Fourier transform. So I'll just go to FFT. FFT of whom? That is our waveform is on channel 2, that is unipolar RZ format is on channel 2. So instead of source channel 1, I'll keep it as channel 2. Now once the channel is 2, what you do is you bring the waveform position to the center. So I have brought it to the center now. Now you have a FFT zoom which has been seen over here. Here what you can see is this is the FFT zoom option. So it is zoom by x1. Now I can expand the zoom. What I'll do is I'll expand it to x2. Then it is x3. Right, this is sufficient. I can see the waveform very clearly. Now how do I measure the zero crossing of this? Once if you say that if I want to observe the FFT of a rectangular waveform, a rect t by tau is nothing but a sin tau, correct? So the function is nothing but sin, and the zero crossing, first zero crossing frequency will correspond to 1 upon tau, that is duration of my pulse. What is the duration of my pulse? It is 500 microseconds. So it will be corresponding to 1 upon tau, that is 2 kilohertz. Here it is 2 upon tau, it is 3 upon tau, 4 upon tau, and so on. So my first frequency component is going to be 2 kilohertz, second is going to be 4 kilohertz, and so on. Now here you can see a noise spike which has been there. Otherwise it is going to be a sync pulse which has been shown over here, right? Now what we'll do is we'll measure the frequency of this, we'll make the waveform stop. Once again I'll go to the option that is measure, then it is cursor. Then in the source, if I want to go is I have to make it math function. Then I have to go to the type option, that is what you can say is frequency. For the cursor, I'll set the cursor. This is the first cursor, the movement of the first cursor. What I will do is the second cursor, I will move it away. Okay, you can take a reference between the two cursors, or you can take the reading directly of the one cursor. So I am taking directly the reading of one cursor. So I have selected cursor 1. I am making it place at the, that is 1 upon tau, that is 0 crossing. What we'll see is the frequency of 1 upon tau. What is the frequency corresponding to? You can see that it is 2 kilohertz is the frequency. Can you see here? So it's 2 kilohertz corresponding to it. Then I'll move the cursor to the next position. So it is going to be 4 kilohertz, which is going to be the next position of the signal. So it's approximately how much? It is approximately 3 300, correct, 3.100 something. So it's corresponding. You have to place the cursor exactly at the position. So if there is a manual that is error, the error may be in the reading itself. So it's 4 kilohertz, that is cursor position is nothing but 4 kilohertz. So you have to see that this is the 4 kilohertz. You can also observe the amplitude of this particular waveform, that is how much is the magnitude. So for this you can set a reference cursor at the top over here, and one reference cursor I am setting it at the below. So where is the cursor? So this is the cursor where we can set. Now this is a manual measurement which you can do is, so once you are placing the cursor, this manual cursor, it's arbitrary wherever you can place it, and as per this reference now you are measuring the dB value. What is the dB value for a cursor that is you are measuring for? So now here I am taking the delta difference, because I have placed one cursor below here and the first cursor is nothing but over here. So the first dB value which I have to measure is the delta difference which I have to take for. So what is the delta difference? It is nothing but something corresponding to 38 dB something, right? So again the second, that is the sync pulse which you can measure is, bring the cursor, that is don't change the reference, sorry, and then bring the first cursor to the second position of the, that is the sync pulse, and you can take down the dB value of the second pulse, that is 28 dB something you can note down. So you have the notation. This is how you observe the spectrum for the line codes, right? Now we'll come to the second, that is the line code, which is polar RZ waveform. Now before that we'll also observe the time, that is the amplitude of this particular that is the in time domain itself. So what is the amplitude? The amplitude will say measure, again cursor, I'll say source, it is channel 1. So channel 1 I want, I'll say amplitude. So here the amplitude for the channel 1, it's nothing but 144. Oh, so this is nothing but your channel is being multiplied somewhere by 110. So you just remove the multiplier. Where do you press? Press channel 1 of the CRO and then come to the probe, that is multiplied by 10, make it multiplied by 1, and then once again measure, that is the signal amplitude. So it's auto set. Once again go to measure, then you can say channel, so that is source is channel 1. Type I can make it as frequency, you can make it as amplitude, so it's a peak to peak value. Okay, here it is, ampere has been changed. So if you can say is, we can measure peak to peak value 1. So it's probe in voltage, correct? It's current instead of 1 minute. Right. Auto set. Once again, come to measure, source. So here you can see the peak to peak values which have been displayed. Similarly, you measure the peak to peak value and verify the peak to peak values, right? Now we'll come to the next option, that is polar RZ option. Now here you can see that is the polar waveform. What is the polar waveform showing? That for half of the duration it is TB by 2, that is positive. Next it is half by duration 0, then it is again for 0 it is minus A by 2, and then it is plus A by 2, minus A by 2, then it is plus A by 2, so on. So this is what you have is the polar. Then comes the bipolar NRZ AMI version. What do you call it as? Alternate mark version. For alternate one, the amplitude is inverted. Now you can see here. See, for first logic 1 amplitude is plus A, for 0 it is 0. Then for next logic 1 amplitude is minus A, for next logic 1 amplitude is plus A, for next one amplitude is minus A. So this is bipolar NRZ alternate mark inversion. Then the last one is nothing but split phase Manchester. For split phase Manchester, you can see that for plus A logic 1 plus A by 2 for the first half duration, minus A by 2 for the next half duration, and again it is going to be minus A by 2 for the first half and plus A by 2 for the next half. So logic 1 plus A by 2 first, minus A by 2, logic 0 minus A by 2 first, plus A by 2. Again logic 0 minus A by 2 plus A by 2, logic 1 plus A by 2 minus A by 2. So in this way, these are the waveforms and the spectrums which you can see for line coding. Thank you.